Continuing 7.1, an introduction to landslides. So a debris flow contains particles that are up to boulder size, supported in a sediment water slurry. Mud flow is debris mixed with water with a high proportion of mud. Basically, mud flows have more mud. Okay, so the image below, is it a mud flow or a debris flow? Based on the picture alone, I'd say it looks like a mud flow. Now, how about this image? Mud flow or debris flow? FYI, the person is no one I know. So there seem to be a lot of boulders. So I'd label this as a debris flow. See how the boulders are supported by the smaller sized particles? That was the sediment water slurry when the whole mass moved. Now that it's dried out, it's mostly just sediment. Next, and fastest flow, avalanche. Very rapid, like 100 feet per second. It's a combination of snow, ice, debris, rocks, soil, vegetation, etc. See the avalanche in the image below? We could hear it too if the image also captured sound. Note, usually when we think of avalanches, they have a lot of snow and ice. That is usually the case, but technically avalanches don't have to have snow. So how would this be different than a fall? Well, there is still a slope for it to rapidly move down, not just free fall off a cliff, though it may flow over a cliff on its way down. The last type of landslide we will discuss is the complex landslide. It is a combination of slides, slumps, and flows. Can you match the features in the cartoon on the left with the features in the picture on the right? And see some possible scarps from slumping near the top of the landslide? See the flow features towards the bottom of the slide? The picture doesn't capture the toe of the slide, but if it was a perfect complex landslide, it would have a toe. So in summary, here's our types of mass movement that we went over. Here's another summary. This one is from an old version of the book. The new version is corrected. Take a moment to review the different types of landslides and other downslope movements. I think the labeling makes sense, but it may take a bit of a review to make it make sense to you. Moving on to forces on slopes. We are going to go through some terms first, and then look at a diagram. First term, driving forces move materials down slope. The weight of slope material is split between downslope and normal force and is increased by things placed on the slope such as vegetation, fill material, or buildings. Second term, resisting forces oppose downslope movement. The shear strength of a potential slip plane is the resistance of material to sliding or flowing along slip planes and is proportional to magnitude of normal force. Here's the diagram. Let's look at it a bit. So we have a downslope and we have a potential slip plane, the thin black line. Which really represents area, i.e. plane, because the line goes into and out of the screen. Just like our hill is actually a volume of sediment. We have marked the center of mass of that sediment with the weight force pulling straight down. But the weight is actually broken into two forces, the normal force N is the force into the hill, and the downslope force, D, parallels the slip plane. This should feel very much like a physics problem. Don't worry, we are just qualitatively describing the forces on the hill. I'm not going to have you do any math. Just understand what's going on. Now, the resisting force is really just the friction along the potential slip plane in the opposite direction of the downslope driving force. Now let's look at the potential road cut at the toe of the slip. The darker downslope driving force. The darker orange area is going to be removed. As a result, some of the slope mass will be removed, which will lessen the weight of the slope, meaning that the downslope force and the normal force are going to be reduced. Good, right? Less weight, less likely to slide, right? Let's see. The road cut will also reduce the area of the potential slip plane. Remember that it is only the friction along the slip plane that is keeping the slope in place. When the plane area is reduced, the total friction is also reduced. So is the weight reduced enough to compensate for the reduction in total friction? Well, if this slope was only just barely stable, the answer would be no. When a road cut is made into the base of the slope, only a little bit of the mass is removed. And a relatively large area of the slip plane is removed. Can you see that in the picture? Takeaway message. The base of the slope is critical in keeping the rest of the slope in place. Undercut a slope and the whole slope could be on top of you. Hopefully, this makes intuitive sense to you. Think of building sandcastles, and then remove a bit of sand from the bottom, and the whole thing falls down. Remove a bit from the top, and not much seems to happen. Remove a bit from the bottom and put it at the bottom, or a bit from the top and put it at the bottom, and your castle is more stable. So, where would be a better place to put the road cut? Right. Closer to the top. And the mass that you remove, place at the bottom of the hill. And don't cut through the slip plane, which is much easier said than done. Another term, safety factor, SF for short, is the ratio of resisting forces to driving forces, meaning in a ratio, resisting forces on top and driving forces on the bottom. A slope is stable when greater than 1, unstable when less than 1. In other words, if the resisting forces are greater than the driving forces, the slope is stable and the safety factor is greater than 1. If you don't believe me, assign a number to resisting forces. Got it? Mine is 6. Now, assign a lower number to driving forces. Got that? Mine is 3. Now put resisting forces in the numerator and driving forces in the denominator. My ratio looks like 6 divided by 3, which is a safety factor of 2. My slope is stable. An unstable example is 4 divided by 8 equals 0.5, which is less than 1. Unstable slope. Unfortunately, slopes are not static, meaning that slopes change, and there are many things that can change them. A previously stable slope can become unstable. What factors might make an area more prone to landslides? Many things, depending on earth material, slope and topography, climate, vegetation, water content, and plain old relentless time. Forces on slopes. Earth material type. First, let's consider mineral composition. Rock is under the slopes, and rocks are made up of minerals. Different minerals make different rocks. For instance, clay minerals, top left image, are flaky, and they are a part of flaky shale, seen in the top right image. Quartz minerals are chunky, bottom left image, and they are a part of strong, solid granite, bottom right image. Now, which rock mineral combination do you think would fall down easier? Obviously, the shale. Degree of consolidation also plays a big role in determining types of potential landslides. Rockfalls are common in consolidated materials that form cliffs. Slumps are common in unconsolidated loose materials. Soil slip occurs when unconsolidated materials are over bedrock. Earth material type also plays a huge role in slip planes. The presence of zones of weakness are slip planes, which are natural breaks in the consistency of materials. These include bedding planes in sedimentary rocks, especially daylight beds, as we discussed previously. Weak clay, mudstone, volcanic pyroclastic material, and shale layers. These all have small minerals in them, many of which are platy in shape, i.e. flat, i.e. prone to slide past each other. Foliation planes in metamorphic rocks, as discussed previously. Fractures, faults, old landslides, these are all previous breaks in the earth material, obviously zones of weakness. Colluvium and alluvium are unconsolidated sediments. Of the two, colluvium is less consolidated. Weaker rock under more resistant rock. Think of sliding bricks on sand on an angle. And the regolith bedrock boundary, which is a typical zone of weakness for soil slips as we discussed earlier. Phew! Don't memorize all this unless you want to. Just know a few examples of potential slip planes due to zones of weakness, and be able to explain why they are weak zones. If you need to, listen to this slide again and/or read it in your textbook. The last earth material type characteristic that concerns us in relation to landslides is permeability, i.e. the ability to transmit water. We've mentioned this before. Soil slips occur when layers have contrasts in permeability, i.e. buildup of water in more permeable layer. This increases weight in the waterlogged layer, as well as aid in loss of cohesion in unconsolidated sediments. So in summary, the things we care about in earth material type that affect the landslide hazard include mineral composition, degree of consolidation, presence of zones of weakness, and permeability. And, due to our lengthy discussion, you know why. If you don't, review it.